Good morning, everyone. We are now on to the last section in chapter 6, section 6.4. For me, it's still the middle of the summer, but trying to get some stuff done. So, section 6.4 talks about independence in these mathematical formulas, and we'll also give you another tack onto the multiplication rule. So, I have a little example here again, straight from the book. What we had was two little experiments. The first one, they were both the same experiment, actually. What was happening is they gave everyone 2 cups of water. One had bottled water in it, one had tap water in it. And they drank the two waters, and then they had to see if they could identify the difference. Basically, can they identify the tap water versus the bottled water? These bottled water manufacturers were hoping to prove to people that their water's better, basically. So anyway, the first one has can you identify the tap water? You can see yes and no, and based on whether or not they drank bottled water in the first place. So the other condition here was people either drank bottled water regularly or not. And you can see the bottled water drinkers, there were 30, 24 out of 30 were able to identify the tap water, and 36 out of 70 were able to identify the tap water if they didn't. And then they just ran the same thing. These are the same 100 people back, actually, in the second one here. It's the same 100 people, but now we separated them by male and female. So you can see that 21 out of 35 males were able to identify, and 39 out of 65. The question for both of these is there a difference? Are they independent, right? So the basic overriding question is, are drinking water, bottled water, sorry, should have that, are drinking bottled water and identifying tap water independent? And then the next question down here at the bottom, whoops, sorry about that, is, are gender and identifying tap water independent? Most people, I hope, if I just asked usually in class right now, I would ask how many people think they are or not. A lot of people will come to this one and say that if the drinking water people were 24 out of 30 could identify, and 36 out of 70 could identify it if they didn't. So this is around 50%. This is way higher. So they're going to say clearly there's a difference. Therefore, they're probably not independent. And then down here, you got the males could do it at a rate of 21 out of 35. The females could do it 39 out of 65. We need a little bit of help here with those decimals. So 21 divided by 35 is 60%. Probably should have been able to do that with a calculator. And 39 divided by 65 is also, hey, look at that, 60%. They're the same. So no difference between males and female. So we're going to look at this a little bit more mathematically. Okay. Whoops. So the mathematical definition for independence looks like this. All right. A and B are independent events if and only if the probability of A given B is equal to the probability of A, and then also the probability of B given A is equal to the probability of B. So they both have to work. Basically, what this says is the probability of A given B is equal to the probability of A. That it doesn't matter whether B happened or not, right? So if you said, what's the probability of drinking or identifying tap water given that you're male is equal to the probability that you can identify tap water, basically means it didn't matter whether you're male or female. So that's the mathematical definition of independence. All right. So basically, we learned. Well, let's do this. So we have what's called the multiplication rule for independent events. So if two events are independent, okay, if two events are independent, one's not impacting the other in any way, shape, or form, that we can just multiply those two probabilities together. So the probability of A happening and B happening is just equal to the probability of A times the probability of B. If I say, what's the probability of getting a heads on the flip of a coin and a 6 on the roll of a dice, you can just multiply those two probabilities together. Okay. Typically, we don't really want to consider whether they're independent or not. So if we go back to, let's do this. If we I asked this little question, why here is, yesterday you had this formula. That was the probability of A given B equals, for a conditional probability, right? The probability of A and B over the probability of B, which you could then rewrite. Sorry about this. Just ignore this down here for right now. If you rewrite this, let's come up here a little bit, you wind up getting the probability of A given B, which we had yesterday also, times the probability of B equals the probability of A and B. But remember, if they are independent, the probability of A given B is just the probability of A. So this winds up being probability of A times the probability of B. So you don't really need this separate formula, but this is very specific. If the two events are independent, it's going to be really easy to just multiply the probabilities together. Don't get too carried away because you got to make sure they are. So this comes into play in a little example here, which is kind of powerful actually, as I have this chart. I know that 42% of all the people in the world have type O blood. 42% have type O blood. So now I have two. It's kind of like flipping a coin, 50%, but this time it's not 50, it's 42%. And the question is, I have two people that I pick from this population. I want to know what's the probability exactly one of them has type O. So the nice thing about this is because these two people, let's assume they're independent, they probably are independent unless they're related or something like that, but they're going to be independent, is I have this little chart here, but I have nothing in the chart, right? I can't, there's no information from the chart, but I'm building this chart myself. I can actually fill that number in there right now because the probability, if I just think about probabilities instead of people, we'll call it like one person. You could put 100 here. Let's put 100 here to make it easier. That probability that goes right in this chart right here, it's the probability of both of them having type O. I can just multiply those two probabilities together, right? 0.42 times 0.42. That's this formula again, right? If they're independent, I can just multiply them together. So let's fill this in. So nice, I can just fill in the chart. I go 0.42 times 0.42, and I get 17.64. Oops. 17. I can do this for any of these boxes, right? So let's say if I go not O, it would be 58% times 58%. So if I come in here, 0.58 times 0.58, and I get 33.64. And I can continue, right? The O not O would be 0.42 times 0.58 because one has it, one doesn't. So 0.42 times 0.58 is 24.36. And this has to also be 24.36, yeah, because it's the 0.42 times the 0.58 also again. And then I can fill in the totals, and then I can answer any question. Probably exactly one of the two would be, let me change colors for you here, exactly one of the two would be that has one, and that's one, right? So we can just add those two up, and you get 48.72. You can also do this with a tree diagram, which might actually be easier than the chart, believe it or not. So the first person, 0.42 for O, 0.58 for not, and then same thing here, right? 0.42, 0.58. 0.42, 0.58. And because they're independent, you can just multiply straight across. You wind up getting the exact same numbers, right? 0.42 times 0.42 is that 0.1764 and so on. I'm not going to fill them all in. Same exact numbers you would have got there because you're just multiplying the same ones together. So the fact that they're independent makes it pretty powerful and pretty easy to go through. So let me give you one little other idea, and then I'll do an example for you. Just independence and mutually exclusive. You've heard those two words, both in this chapter. I'm going to try to put them together a little bit. Hopefully this doesn't confuse you. Remember that independence means they're not connected anyway. One's not affecting the outcome of the other, whereas mutually exclusive means they both can't happen at the same time. So sometimes people have a little... sorry, that disjoint should go with mutually exclusive, so just ignore that there. So sometimes people have a hard time with this. Mutually exclusive, they both can't happen at the same time. Independence is one's just not affecting the other one at all. Okay. So, for example, if two events are mutually exclusive, they actually have to be dependent on each other, because if they're mutually exclusive, they are impacting each other, because if they both can't happen at the same time, if one happens, the other one can't. That means this one is dependent on whether this one happens or not. So they're not the same idea. As a matter of fact, if they're mutually exclusive, they can't be independent. Well, there's a weird example, which we won't get into right now. So if I ask you, let's go back to the original problem here, and I said, are they independent? If someone says, are they independent, what you're going to do is test. So you're going to go the probability of, we'll just pick one. I'm going to go up to the top one, right? We're going to go to the top one. So we'll go drinks bottled water, given can identify. I'm just going to go find that probability. Drinks bottled water, given that they can identify. So these are the ones that come out at 60, 24 out of 60. Can do that. So then if they are really independent, remember that this has to equal the probability drinks bottled water, because whether they can identify or not doesn't matter. Remember, that's the idea of independence. Probability of drink bottled water is 24 out of, it's 30. Drink bottled water, that's that 30 out of 100. So the 24 out of 60, we'll do a little quick, I know I can probably do this in my head, is 40%. This is 30%. Not equal, therefore not independent. Okay, that's the idea of showing. So if someone asks you to show independence, if they happen to be equal, flip them around and see if they're also equal. They both have to work. Okay. This also sometimes begs a question like, man, what if they're really close, right? So there is a little minor problem here. So let me show you just one quick example, and I'll be done. This one was a baseball coach wanted to know if his team played better at night or during the day. So what you have here is whether or not they won the game and whether or not they were playing it during the day or at night. Okay. So if we do some math here, probability of winning is 41 out of 78. So winning, you can see the one in the game is the 41 out of the 78. Okay. Probability of winning, given that it's a day game, is given it's a day game. So day game are these, try that again. Day games are those guys. 21 of them, they won 11 of those. So notice 52.56%, 52.38%. By our definition, they're not equal. Therefore, they're not independent. However, if you think about this logically, that's kind of nonsense. If the baseball manager is interested, he's going to say there's no difference, right? They're so close that we're not better during the day than we are at night. And also, sometimes these numbers can never be exactly equal with like a sample size of 78, because the percents aren't going to come out perfect, right? So we run into a little bit of problem, right? That it's hard to show independence with real data. So if this were our class and this happened, I would say yes, close enough, right? But then that begs the next question, that how close is close enough? If one was 52 and one was 51, would I say it? One was 52 and one was 49, would I say it? So it can get a little confusing for sure. We'll talk more about that later on in the course. But there's also a much better test for independence coming later. But for right now, to test independence, we just go back to this little, if I can find them here, this one right here, right? If they're independent, probability of A given B equals probability of A and vice versa. So you have to check them both. That's it for chapter 6, section 6.4. A little bit of homework on this if you're watching this, and then a little practice per se test on chapter 6 to see how everyone's doing. Hope it was all right. Let me know if you have questions.